Okay, Roz, let's take a look at some sketches of reciprocal trig functions. We're going to sketch and state the domain of range of a couple of curves. Let's start with f of theta equals the secant of theta. We want to make sure that we're not confusing definitions with identities. The definition for the secant of theta is the ratio of r to x. R divided by x doesn't exist when x is equal to 0. The reciprocal of the cosine of theta also doesn't exist when x is equal to 0. And that means that this curve is going to be equivalent to the reciprocal of the cosine of theta. And that's likely how I would draw a sketch of this curve. I would sketch a cosine curve first. Probably a little bit shorter than normal because I know that my sketch of my actual curve is going to be outside of here. I don't want to use up all of my space for my frame now because the reciprocal curve is going to be outside of there. An original cosine curve has a period of 2 pi. Let's get our key points on here. Key inputs. And we're going maximum axis, minimum axis, maximum. Something like that. And now let's start reciprocating values. We should be able to do this in standard position as well. That if we have an angle of 0, then notice that the ratio of my x value to my r value is going to be 1. If I have an angle of pi by 2, then the ratio of r to x is not going to exist. As I get closer here, as I divide by numbers that get closer to 0 from values larger than 0, I would expect my ratios to increase without bound. And that's why it follows the same path as the reciprocal here. The reciprocal of 1/2 is 2, and the reciprocal of 1/4 is 4, and the reciprocal of 1/10 is 10, and the reciprocal of 1/100th is 100, but I can't reciprocate 0. So I don't memorize that we have a vertical asymptote at theta equals pi by 2. I observe, I discover that I have a vertical asymptote there. Now this shape is not parabolic because parabolas don't have asymptotes. Okay. The reciprocal of -1 is -1. The reciprocal of -1/2 is -2. The reciprocal of -1/4 is -4. There's symmetry about the line x equals pi, or theta equals pi, on this curve, so there will be symmetry in its reciprocal as well. I draw a curve that looks a little something like that. Vertical asymptote at theta equals 3 pi by 2. And then my outputs change from being negative to positive. So my reciprocal changes from being negative to positive. And it looks a little something like that. And I get a curve that has an axis of the curve of y equals 0. It's halfway between my maximum and my minimum. But my function has no roots. Okay. My function still has a period of 2 pi. Its domain is the set of all theta values that are real numbers, goes left and right forever, and there's an infinite number of possible theta values. But theta cannot equal pi by 2. Theta cannot equal 3 pi by 2 or 5 pi by 2. The distance in between restrictions here is going to be a half rotation, or pi. That's my common difference in this arithmetic sequence. So I add integer multiples of pi. And that creates the family of values that theta cannot be, just like the family of roots of the cosine curve. Okay. For the range I see on my sketch, looks like outputs, I'll call them f of theta, are real numbers. And it looks like there's 2 separate areas here, so I should write 2 separate restrictions, just like 2 separate intervals. I'm going to say sometimes f of theta is greater than or equal to 1, or some other times f of theta is less than or equal to -1. There's 2 ways that I know that I can't combine this into one statement. One is I can't draw this with one interval, and 2 is it would be nonsense if I tried. Sometimes students say, oh, look, there's f of theta, and the alligator wants to eat the 1, so we'll put that there, and oh, the alligator wants to eat the -1. And this statement is saying that 1 is less than -1, which is nonsense. It's not and. We're not satisfying both of these conditions at the same time. It's or. We are satisfying one condition or the other condition. Either. Outputs are either greater than or equal to 1, or they could be less than or equal to -1. Okay. I know in English we sometimes say, oh, look, outputs are bigger than 1, and sometimes they're less than -1, but you can't be both at the same time. Okay. Let's try the cotangent curve next. G of theta equals the cotangent of theta. Now, we saw when we were finding exact values that we can find the cotangent of pi by 2. That's because the cotangent of theta is not the reciprocal of the tangent of theta. Not always. It's not always not equal to as well, I guess. The definition for the cotangent of theta is the ratio of x to y. Now, I may have used the reciprocal of the tangent definition to help me remember this, because it is just a definition. Notice that in this case, x can equal 0, but y cannot equal 0. I can't calculate the tangent of theta when x is equal to 0. I can calculate the cotangent of theta when x is equal to 0. This x and this y, by the way, are standard position x and y. We have two different graphs here. We have up here, this was my x-axis and y-axis in standard position. This was my theta axis and my f of theta axis. Having them labeled and not always using x as your input. Like stating the domain here on x is problematic because there's another x on the page. Okay, so let's see what we can do just with this definition here. I'm going to draw the theta axis. Because I know the cotangent curve, sorry, exists around there sometimes. Let's put in my dependent axis as well. Why not? There's g of theta. Okay, let's see what we can sketch from 0 to 2 pi. There's a pi right there. There's a pi by 2. And maybe about there, 3 pi by 2. I might be interested in inputs of pi by 4 for this specific function. Right here, y is equal to 0. On a circle of radius r, I'm going through r comma 0. So right away, the cotangent of 0 doesn't exist. If I rotate to here, this is 0 comma r, the ratio of x to r is going to be 0, or x to y is going to be 0 to r. So I have a root at pi by 2. We'll sketch the reciprocal of the tangent curve in a second, and we'll discover it doesn't have any roots. When theta is pi, our y value is 0. That's a restriction on this function, so my function doesn't exist. After 3 pi by 2, 0 comma negative r, my x value is 0 and my y value is not, so I have another root right there. And then my function doesn't exist again. This isn't a lot to go by. I mean, we could anticipate that we probably have vertical asymptotes because we've seen a lot of vertical asymptotes for the last couple of days. But let's do a little bit better. Let's go with our related acute angles of pi by 4. These create right isosceles triangles, or we're along the line y equals x or y equals negative x. Y equals negative x. So after a rotation of pi by 4, my ratio of x to y is going to be 1. So I'm going through pi by 4, comma 1. I'm going through 5 pi by 4, comma 1 as well. That's 4 pi by 4, 5 pi by 4, comma 1. I'm going to be passing through 3 pi by 4, comma negative 1, because the ratio of y to x is going to be negative here. I don't need cast rule to tell me that. I know I'm on the line y equals negative x. So the ratio of x to y is going to be negative 1 at 3 pi by 4. Negative 1. And the ratio of x to y is going to be negative 1, again, at 7 pi by 4. That gives me a little bit more information. I can then realize that as x approaches 0 from values that are greater than 0, as I get close to pi by 2, my outputs should, as I get close to 0 from values that are greater than 0, my outputs should increase without bound. So I come down here, cross there. Here, let's do another one. As theta approaches pi from values that are less than pi, y is approaching 0 from values that are greater than 0, which means that the ratio of x to y is going to, oh, and x is negative. That means that my ratio of x to y is going to get very, very small. That's my best sketch of the cotangent curve. I'm not as good at sketching tangent curves and cotangent curves. I don't have as much practice. Domain and range. Domain here is the set of all theta values such that theta is a real number, but theta can't be 0 or pi or 2 pi. That means that theta can't be an integer multiple of pi. That's how you list an infinite number of restrictions. The range, though, isn't super exciting. The curve goes up forever. The curve goes down forever. Outputs g of theta can be any real number. Okay. Now we call the cotangent of theta a reciprocal ratio, and we might refer to this as a type of, it's a graph of a function given by a reciprocal ratio, but it's not a reciprocal curve because it has roots. There's no value that I can reciprocate that would give me roots. Cotangent of theta has roots because cotangent of theta's definition is x divided by y. And at pi by 2, x is 0 and y isn't. Okay. By definition, it has roots. So let's look just real quick here at how the reciprocal of the tangent function would be different. Let's say we are going to sketch h of theta is the reciprocal of the tangent of theta. So it would be a serious mistake if we were to just sketch the cotangent curve. Let's look at the definition here. This would be the reciprocal of y over x. Now, the restrictions on the ratio of y over x are that x can't equal 0 because I'm dividing by x, but also y can't equal 0 because I'm dividing by y. Got it? I mean, you could write down that the reciprocal of y over x is x over y, but these restrictions still remain in place. X can't equal 0, and that's how this is going to be different. We don't need to logic through it like that, but it would work just fine, I suppose. Let's try drawing this by sketching the tangent curve instead. The tangent curve, let's see, the tangent of 0 is 0. The tangent of pi by 2 does not exist. The tangent of pi is 0. The tangent of 3 pi by 2 does not exist. And the tangent of 2 pi is 0. Again, there's y equals 0. That's the theta axis. Right, and tangent ratios when x and y are positive. Of course, tangent ratios are positive. Sign change occurs. Sign change occurs through a root. Sign change. There's the tangent curve. That's I should probably label that. That's y equals the tangent of theta. And here comes the reciprocal. The reciprocal of 1 is 1. The reciprocal of 1/2 is 2. The reciprocal of 2 is 1/2. The reciprocal of 1/10 is going to be 10, so I see divergence towards a vertical asymptote. The reciprocal of 10 is going to be 1/10. The reciprocal of 100 is going to be 1/100th. The reciprocal of 1,000 is going to be 1/1000th. But there's no output here. There's no output for me to reciprocate. What I understand, though, is that I am converging towards 0. Like that. Then I reciprocate -1 and get -1. I reciprocate -2 and get -1/2, and -4 and get -1/4, and -1/10 and get -1/10, and -1/2 and get -2, and -1/4 and get -4. And I can't reciprocate 0, but as my outputs approach 0 from values that are less than 0, my outputs should diverge towards -infinity. It looks like I'm heading towards 0, but I ask myself, what output did I reciprocate? There isn't an output. The reciprocal of something that doesn't exist isn't going to be 0. I have to have something to reciprocate. This is a reciprocal curve, and reciprocal curves with a no root in the numerator will never equal 0. wait a minute, we look back here and we say, isn't there a possibility of a root in the numerator? No, no, because x can't equal 0. That's really the only difference between these two curves, but it's a very big and a very small difference at the same point. Look at the blue curve here and the black curve up there. I'll try to zoom out. Okay. The cotangent curve kind of goes swoosh, swoosh like that. The reciprocal of the tangent curve goes swoosh, swoosh like that. The only difference is the cotangent curve has roots. The reciprocal of the tangent curve has holes. Now don't try to memorize that because you might be asked to explain it. Let's label this and find a spot to squeeze in its domain and range, I suppose, because its domain is kind of interesting. It's going to be the set of all theta values that are real numbers. And then I notice that theta can't equal, I didn't label my asymptotes. Theta equals 0. I guess I could label this whole pi by 2 comma 0. Theta equals pi is another asymptote. That's 3 pi by 2 comma 0, a hole there. I've already labeled that input on my original curve, and the output is already labeled, so I mean, I guess I should still label them. And then this is going to be theta equals 2 pi. Now, for your domain, and I've ruined my space, I'll go down here. You don't need to identify a difference between vertical asymptotes or holes. Theta can't equal 0, or 2 pi, pi by 2, or 2 pi by 2, or 3 pi by 2, or 4 pi by 2. So the fastest way to say this is that theta can't equal pi by 2n, where n is an element of the integers. And this should make sense from standard position. If we can't have x or y equaling 0, then our angles can't be coterminal to the axes. 0 pi by 2, 1 pi by 2, 3 pi by 2, 4 pi by 2, 5 pi by 2, and so on, and so on. Range. A little more interesting than the cotangent curve. It's the set of all outputs, h of theta, that are, of course, all real numbers. Except, now it goes up forever, it goes down forever, but notice it'll just never be 0. No horizontal asymptote here. It's a periodic function. Its end behaviors are, let's just say it's periodic, keeps on going. But yeah, never going to get an output of 0. H of theta cannot equal 0. Okay, there would be too much to memorize here, so it's probably best to try to understand it. Give that a shot.